Okay, continuing on. We talked about angular dimensions. Now let's talk about dimensions of holes. Okay? So we're talking about drill a 1/4 inch hole made with 1/4 inch drill and a 1/4 inch in diameter. Counterbore hole designations, diameter of the drilled hole, diameter of the counterbore, the depth of the counterbore, number of holes to be drilled. So, in this case, here is what we're using. Okay, drill 1/2 inch through. This is very typical, so that means the entire hole is going to be a 1/2 inch all the way through. If it does not say through, it may tell you 1/2 inch by 7/8 deep or 3/8 deep, whatever. If you see the word through, that means it goes entirely through the plate. Okay? Your counterbore is 3/4 of an inch wide, so that's in your diameter, by 3/8 of an inch deep. Okay? And as you see, typical for all three holes. Okay. Countersunk holes. Same thing. 1/2 inch drilled hole through. Countersink 82 degrees. So in the countersink distinguished, it is an included angle of 82 degrees, not a single angle, by 1/2 inch deep. All three holes. So when you're doing drawings, when you get into the drawing section, the CAM portion and CAD and CAM portion of the program, it's important as well that you're making sure they're countersink, not counterbored. Selecting tooling in your prints, your drawings, so forth. All right. Looking at page 982. We are going to talk about dimensions of screw threads and threaded holes. There's two main types of screw threads: coarse thread series and a fine thread series. These are not to be confused with also pipe thread. So you have your normal thread series for bolt patterns, screws and bolts. But then your pipe thread is a completely different measurement as well. So you might see a 1/2 inch by 20 thread count. Then you may see a 1/2 inch NPT. So NPT is what we refer to as a national pipe thread versus the normal bolt thread pattern. Okay? The total thread does not need to be shown on the print. So here's a good example. 60 degrees is included, so a 30 degree each side. 1.5 inch diameter piece. The length of the thread is 1 5/8 inches. 6 threads per inch. So 1.5 inches to 6. National coarse thread. Here's an example of a fine thread. So here's 1 inch, there's 18 threads in each inch of length. Okay? So the other thing that you can do, look at the diameter. The bigger the diameter, usually the further spread out the threads are, even in a fine thread versus a coarse thread. Okay? You might get a 5/8, and I can't think off the top of my head what a 5/8 is, but I believe it's down somewhere around a 12 or a 13 for a national coarse thread instead of a fine thread. And versus 18 for the fine. Okay. Usually you'll see some sort of a markings, and then it will detail that it is a threaded, and it'll give you the dimensions, so forth. Here's another example. So 5/8, so here at 11. 5/8, 11 national coarse. Here is 5/8 for 18 inches, threads per inch for a national fine. Okay. Drawing symbols for internal, conventional or simplified. So let's start here. Uses baseline or a datum surface off which all dimensions are based. So in this case, right here is the datum line. This is the datum surface for x dimensions. This is the datum surface for y dimensions. Okay? So what we're saying is that if we're going to start from one point, especially in particular in layout, all right, we can start. We're starting from this point. This right here is 0, 0. This is positive, and then this is a positive dimension as well. So we start from this point. All measurements are made from this point. And so forth. We don't, now does that mean that it can't be made from other points? No, there's sometimes in real life applications to where you may have to go to a 2. Say you don't know this dimension, say this goes 2. This shows you 1. You're going to have to say 2 plus 1 is 3, so then this dimension is going to be 4 minus 3 is 1. You may have to lay it out. You don't always get every detailed print. You're going to have to do a lot of subtraction and addition sometimes to be able to help explain where your print is at. Okay? Now, as you go through, starting out especially beginning, it's usually important to keep your datum at one point. This is usually, for example, in machining, you'll find edge finder here, 0, 0 here. That's the point where you start, everything goes from there. You start getting into the CNC portion and so forth, three-dimensional objects. You may run a datum line that say it's centered. This may be your datum line, okay? So you might have a positive 2 and a negative 2. Say we run here in the middle. We're 2 here, so everything on this value will be a negative, this will be a positive, and we'll get into that Cartesian coordinate system later on in other programs as well. But you have to have a starting point, what we're referring to here, 0, 0 is here, everything is made from this point, don't make it from the opposite direction for the most part. Okay? Tolerances. Limits of tolerance, that's the permissible range of variation in dimensions, completed job. That's basically, to translate it into slang terminology, that's basically how much of an error you're allowed to have, okay? How much swap within the part, how much off it can be. If it's supposed to be, if it can only be off of 1/8 of an inch, that's your tolerance, so forth, all right? So an example, one limit of tolerance is plus or minus 1/32 of an inch. Now machining it may be 5 thousandths. Okay, so it might be 0.005. In welding, for the most part, we're dealing with 30 of an inch. Is usually one of the smallest numbers that we're going to be dealing with for the most part. Okay. So what we can see here is it can be plus or minus 1/32. So real quick. Let's say that it's defined as 1-inch weld plus or minus 1/32. So you're allowed from, if it's 1 inch, you're allowed 1 1/32 of an inch, or you're allowed 31/32 of an inch. 1 inch above, or 1/32 of an inch above 1 inch, or 1/32 below. That's your tolerance range because it's giving you a plus or a minus. So it's either higher or lower. Okay? Ratio between the actual size of the drawing and the actual size of the object. Full size is 1:1, so the drawing's the exact same size as the object. Many objects are too large to do full size. They're scaled drawings, so 1/4 inch to 1 means drawing is made 1/4 the size of the object, or even more. Okay, maybe a 25:1 scale, 1/100th of a scale, something like that, depending on what we're working with. Okay. Symbols and abbreviations. Symbol's a simple picture that represents an object or idea whose purpose is to condense information. Abbreviations are basically just a short and condensed way to explain something. We've seen earlier, right here, this is an abbreviation, THRU. We know it's spelled THROUGH. This shortens it up to where you might be able to fit it on there. Okay, this is drill, DR for drill. Countersink, we didn't spell out the counter. We use abbreviations quite often. You can go to table 29-5, which is on page 984. And here are drawing symbols and abbreviations, okay? Pretty interesting table. There's some things there that you may not understand. There are things that you'll see on prints. This is always a good page to come back to be able to understand the abbreviations when you're looking at a blueprint if you're confused. Okay, geometric shapes. Okay, a circle. Most everybody knows what a circle is. It's a round, perfectly round shape. All sides are equally dimensioned. Line C is the circumference, so it's the entire distance around the object. Okay. Lines B run through the center, the circle, and they're called your center lines, depending on which axis you refer them to as well. It might be, in this case, this is a horizontal line. This is vertical, the way we're looking at it here. Line D is the diameter, so the distance completely across. And as you can see, R is half of the distance of the diameter. Only 1/2 of that. Okay, geometric shapes. Moving on. I know this seems simple. A lot of us know this very well. However, we're going to cover it fairly quick. Okay. Rectangles. It's where 4 sides. It is a square-looking box. However, 2 sides are the same distance. The other 2 are opposite distances or opposite lengths. A square is the rectangle where all 4 sides are of equal length. Okay. So something to be aware of is a rectangle has all 4 corners as well as a square are right triangles. Opposite sides are parallel to each other. These 2 sides are perpendicular to each other. Diagonals, straight line connecting opposite corners. Therefore, this right here is the center point of the entire rectangle. Okay. Triangle. It's a flat figure of 3 straight sides. So this is an equilateral triangle to where all 3 sides are equal and all 3 angles are equal. Okay? This is a right triangle where one side is square. So when we say square, we know that this angle is 90 degrees. All right? So, real quick, very important to understand on a triangle. If it's a triangle, it's a 3-sided piece, okay? All 3 angles have to combine to make up 180 degrees. So in this case, we have a 90-degree piece, so we know that these 2 angles combined make up 90 degrees, all right? In this case, they are all 3 the same, so we take 180 divided by 3. All 3 angles are 60 degrees combined. Okay? Gauges. I'm going to read from the book a couple things real quick. Page 985, left-hand column underneath the gauges. Excuse me. There are two gauges in common use for measuring the thickness of metal. The U.S. standard gauge designates the thickness of sheet steel or sheet iron. The B&S, the Brown and Sharpe gauge, designates the thickness of sheet brass and copper wire. In both cases, the larger the gauge number, the thinner the metal. For example, 16 gauge is thinner than 9 gauge. Gauge sizes are given in the appendix. So, you feel free to look to the appendix. And it will tell you the gauge dimensions. We're not going to go through them now. The big thing is one of them is sheet steel or sheet iron. Brass and copper have a completely different thickness and designation, a different scale that they use. Types of views. Okay. It's important to visualize and determine relative position in regards to the picture. Earlier we looked at the piece of square rectangular tubing. We had a top view, a front view, and a right side view. With amongst all three of those views, we were able to see and realize that it was a piece of tubing because the top was solid, the side piece was solid, and then from an end view, a right angle view, we were able to see that there were solid object lines on the outside and the interior, meaning the rest was hollow and certain parts were solid. Okay? Let's talk about third angle projection. Means you're moving your eye around a fixed object. First angle projections means you're stationary and moving the object with your hand while holding it up against a drawing surface. The 6 regular views that you're going to see are a front, top, bottom, left, and right sides, and the back side view. More than likely, you see the front, the top, and a right side. But depending on the piece, you may have to change that up because those 3 may not give you enough detail to get there, to be able to understand the 3-dimensional part. Okay? So really simple. We're looking at it from the front. Okay, so coming this side, here's a left-hand view, here's a right-hand view, this is a frontal view, this is the right side, so this is looking here. We're looking down, this is the outside object, that's the interior piece. If we're looking left side, we see this piece first, it's hidden, or a solid object line, so is the outside. Okay, but if you notice on this, it doesn't say that it's a hollow piece. Okay. What this shows me is that this is hidden, so this is telling me that it must be that it is a solid piece because it's showing a hidden line. All right. So right there was a good way to just understand from this one drawing. It tells me it's a solid piece, or that the right-hand side is solid at least. Okay. First angle projection, 3-view drawing. So here's a pictorial view. So this is basically isometric view. You can see it pictorial, like if you were taking a picture. The top, solid object lines. The front view shows hidden lines, so you can see inside the dimension this pocket, and you're looking at the depth. It's one solid distance on both sides. So it's parallel to the top edge. This bottom is. Okay. Right side view, same thing. It only shows one. So we know that this is parallel. Both right here and right here are parallel to the top and the bottom as well. Alright. This is a sectional view. So this might be where the M is showing you the cross section. And it might give you some dimensions here instead of here. Okay? Sectional view shows the inside. Diagonal lines indicate the part of the solid section that would be cut through. So right here we're showing the cross hatching. This is where it's cut. Detailed views. I don't think we had a detailed view here. Detailed view is usually a exploded, more in depth and zoomed in view, I should say. It's used in the scale of the drawing is so small it's impossible to get the clear picture of the object. See the detail sends user to a large drawing of a small area. Okay, let's talk about piping drawings. Specialized, used to show how assembly of pipe system goes together, done with both line and single line methods. It's usually done in a pictorial view. We are now on page 988, chapter 29. So right here it shows you table 29.6, shows you the ANSI pipe symbols, okay? So real quick, if you look at that section, it shows you, for example, that the welding symbol is typically depicted as a X line. So, real quick, usually what it is referring to, I want you to notice that it's showing that a welded symbol, that at these joints the X means welded versus flanged or a screwed fitting. Okay, flange means the two pieces bolt together. Screws means it threads. There's a pipe thread usually there, and that's how it connects to the pieces. Over here as well, flange screwed or welded pipe shows you a lateral pipe plug, reducer, so forth. Hopefully we'll get a chance to go through those. If not, I want you to make note of them yourself. If you would like to draw them on your notepad, would probably not be a bad idea. So what we've seen here, what it's showing and referring to in this section, is that the dot is often used instead of the X to indicate a welded joint. This is fairly common nowadays, especially because you get a lot of X's and things going on, and you got an X right here and an X right here next to the valve, and sometimes it gets confusing of, is that, what does that mean? Is there more valves there? Or is it a double check valve? What do we mean? Okay? So in this case, what we're doing is just showing a print. This is a real life drawing, what it should be. Here's going to be your single line pipe drawing, okay? This is typically how you will see it. And then this will be sent, this might be denoted as, in a larger print, it might be valve 1. Then you'll go to the note or the material supply and detailed section, and it might say valve 1 is a 2-inch, 160-pound valve, gate valve, not a ball valve, have extra information or so forth, okay?